Hello to everybody, and welcome back to my SP2 channel. So we're going to be looking at ionization energy, the definition of that, the periodic trends for that, and we also have a practice at the end. Okay, so starting by kind of definition of ionization energy. So think about how easy we can remove an electron from an atom or maybe an ion, and that can help us to understand the reactivity or even the chemical behavior of our species, right? So the ionization energy is presenting the minimum amount of energy that is needed to remove an electron from the ground state of an ion or an atom, and it has to be always in the gas phase. So it must be gaseous species. Okay. Now, because I need to add energy, always like investing energy to remove that, you can think about all of your ionization energies that are going to be a positive value, right? You can always call them endothermic process, right? Now, the idea of ionization and making ion originally, like for the very first time, was introduced by Bohr model, if you remember that. And they found that if they add enough energy to remove an electron, or let's say to excite an electron from N1, the ground state, to infinitive, right? That is going to be the way that they can turn that hydrogen atom to an ionized species. Okay, cool. Okay, now in general, the first ionization energy is the energy required to remove the first electron, right? And that starting point is going to be your neutral atom. For example, if you're looking at something like sodium, you go from a gaseous sodium, right? You add energy and you remove that electron and you turn that to sodium cation, right? You can also go ahead and add even more energy to remove the second electron, right? So the second ionization energy is going to be from the cationic form, right? So we have sodium cation, we're removing the second electron and we turn that to Na2 plus, right? Okay, so if you think about the definition of ionization energy one more time, it's indicative of the amount of energy needed to remove an electron. That means if I have a greater ionization energy, it signifies that it was more difficult to remove that electron, right? So for the ionization energies of a given element, it is always going to increase as we progress because the removal of the next electron is always harder, right? And I hope the logic is clear. This just means that the successive removal, right, is always getting harder and harder because you remove that from something that is positively charged, right? Excellent. Okay, so looking at the periodic trends for our ionization energy. So if you're moving from the left to the right side in a period, the IE generally increases, and that is mainly because of the size that is getting smaller, right? So you would have a stronger pull on your valence electrons, and therefore it needs more energy to remove that. For example, your alkali metals are going to have the lowest ionization energy in each period, right? But the noble gases are going to have the highest one, right? It takes the most amount of energy to remove an electron from a noble gas. Now, if you're moving down a group, right, the IE1 generally decreases, right? For instance, if you look at your ionization energies for the noble gases, helium is going to have the highest one. As you go down, we are getting larger, and therefore the removal of the electron needs less energy, right? So xenon is going to have the one with the lowest ionization energy. Now, keep that in mind in general, the ionization energies for transition metals increases slightly, right, from left to right in a period. And for the F-like metals, also we have only a small variations in our, first ionization energy. Okay, cool, cool. Okay, that brings us to our practice. So referring to the table, and again, I have that portion of the table that you needed. We're trying to arrange the atoms, neon, sodium, phosphorus, argon, and potassium in the order of increasing for their first ionization energy. So if you look at the table, for sodium, phosphorus, and argon, all three of them are on the same row. Okay, so sodium must be, the lowest one, right? Because that's the biggest one. And then I have phosphorus, and then I have argon. Now, if you look at argon and neon, they are on the same column, right? And argon is bigger than neon, so that needs less energy to ionize. And then if you compare your sodium and your potassium, potassium is bigger, and therefore we need less energy for that, right? And then we're going to put them all together. It would be potassium as the lowest in energy, and then we have sodium, and then phosphorus, argon, and the next one, or the most energy, would be for neon. Very good. Thank you so much for watching this video. If you like it, give it a thumbs up, please. And if you actually want to keep learning with me, the best way is to subscribe. Okay? I'll see you soon on the next lecture. Take care of yourself. Bye-bye for now.